Welcome to Humans of Reliability. I'm Sylvain Kalash, head of the Rootly AI Labs, and your host for today. In this episode, we welcome Tomás Hernando Koffman, the co-founder of non-determinism, a data-driven infrastructure platform for the multimodal future. Let's dive in. Tomás, can you share with us what makes AI system hard to keep stable and trackable and reliable?
I think the answer to that is, essentially these are non-deterministic systems. And so the development process is very laborious, where we maybe come up with a first draft architecture. We choose an LLM based on kind of gut instinct or what we've read online. And then we kind of start hacking around on it. And we find an edge case where something breaks. So we kind of try to fix that. And then we find a different edge case where something else breaks. And then by the time we kind of have something working, a new model has come out and we have to start all over from scratch. And so it's not only very hard to build something that's stable, there's so many different variables and dimensions, but then to maintain that stability over time as the ground keeps shifting under our feet is very difficult.
Yeah, I love it. We are starting strong here. Yeah, like historically, most of the system SREs have maintained, if you have the same infrastructure, same code, same data, you should expect the same output. Right. And here is no longer the case. And I think you've said something like, hey, like, I think you would say this, like, we'd never ship code that would fail 20% of the time, right? Yet that's a type of performance or, failure rate, right? That engineer might encounter when they are building this type of LLM back system. What do you think, are those rate, like, is 80%, something that's like easily achievable? How much does it take, to get to this 9, area? Like, what's the deal with, right, the type of performance that we can expect from the system?
Yeah, I think it's definitely very poignant to be having this conversation on this podcast, in the context of reliability, where really a lot of people would kill for 80%, success rate and accuracy in AI. And that's such a crazy threshold to be comfortable with within the kind of history and culture of what reliability has traditionally meant in engineering. And so I think there's a spectrum here, and it depends a little bit on the application itself. Sometimes it's okay to hit 80% and then to ship and continue improving as you're getting back production data. But really the goal is that we want to get to, 99+% accuracy, certainly above 95% accuracy, because we're deploying these systems at scale, right? It's not like they're handling one task every couple of weeks. The value of AI is that it can deal with hundreds or thousands of tasks every day. So an 80% success rate means, hundreds of failures every day. And I think for us to actually trust our AI systems, particularly in sort of mission critical domains like reliability, like finance, like, health or anything else where we really need to be able to trust the outputs of these systems, the threshold for trust, I think, gets much higher as the kind of importance of the application becomes higher. And so the goal is to get to systems that are 99% plus reliable. And I think that's a big challenge with most of today's tooling.
What's interesting, I'm actually curious, like, which type of application still fine with, like, let's say an 80% success rate?
I think certainly, to start with, if it's a non-regulated application, that helps, right? So regulated industries have kind of much stricter thresholds and performance demands. And then also, generally things that are more subjective or, let's say, soft, like a chatbot, maybe creative tooling, 80% is kind of the threshold where if you're a user and you're kind of having a back and forth and 4 out of 5 of your kind of AI interactions really deliver value much, much faster than if you were to kind of have to go through it all manually. People, I think, are willing to fight through that. And you're probably going to be able to get some kind of users to begin providing feedback and who have enough pain and need to engage. Now, I think that as you move into more kinds of domains like metadata extraction or classification or text to SQL, demands for accuracy become much higher because the outcome of that, especially the less that you have a human in the loop, the outcomes become kind of much more cascading in terms of the impact, right? So if you run, thousands of files with a metadata extraction pipeline that only has an 80% success rate, you've just kind of polluted your data pipelines. So that's kind of a scenario where I think you start to need much, much higher levels of accuracy.
I think what interests us really in this conversation is to speak about, this domain area where we need to reach these nines. So what can SREs do? What tool, strategy, process can help them to get to this nines of reliability? What new practices are emerging?
The first is just, as the baseline is we need principled evaluations if we want to measure accuracy in the first place. And I think that without a way of actually measuring the accuracy or the performance of our applications, if we're just kind of vibe coding and vibe building, it's very, very hard to perceive subjectively the difference between, 83% accuracy and 87% accuracy. But, over the course of hundreds or thousands of LLM runs, that difference really, really matters. So the way I think teams can build evaluations, the gold standard is to have a set of golden outputs or expected outputs. So you have a data set where you say, hey, for this input, this is what we would expect the LM to respond with. This is the metadata that should be extracted. This is the class that should be classified as. This is an example of the summary message or the RAG response that a human expert would generate. And then I think once we have kind of reliable evaluations, which we can take that and then use semantic similarity to evaluate the LM response to the expected response, or if we have other metrics for measuring, say, faithfulness to the context or unsupervised LM as a judge evaluation metrics. There's a huge set of kind of approaches there, and we could easily spend the rest of this conversation just talking about that. But that's the first step. And I think once we have that in place, there's a number of tools. The first is, getting the data that we're retrieving and that we're pulling into the context of our decisions to actually be high quality. And that's not only about retrieving the right data, but then it's also about presenting the data to the LM in a way that is actually tractable. So this is, part of what we, I think, refer to as context engineering. And then we have agent or our workflows leveraging tools. The quality and the descriptions of those tools become also very, very important for the ability to kind of accurately call those and then access external data sources or other functionalities in the course of the application. But the other two pieces that are kind of, I'd say, the biggest levers are which model we're using. And again, there's kind of a new model released every week, and it's very hard to know a priori which model is going to perform best in our use case, and then how we're prompting it. So models are incredibly sensitive to prompts, and the difference between a good prompt and a bad prompt can be the difference between 10, 20, 30% accuracy and 80, 90, 99% accuracy. So those are kind of the biggest levers I look at. Maybe the last thing that I didn't mention there as well is that often our AI applications today are not simple input outputs, but they're compound systems. And so if we have a graph of the workflow of how one call feeds into another call, that also has a significant impact on accuracy. So, it's a matter of kind of getting all of the pieces of the puzzle very high quality individually to kind of drive very strong end results. And then it's about iteration and optimization.
So today we are going to focus, as you said, there are many, facets, like sides to this equation. But today we are going to focus on one of them. And I think it's quite interesting when you think about it, when you are using LLM to power this application. Okay, you have your model, but then there is a lot of, the way to run it is to, give it a lot of instruction and data, right? And you have actually multi-layers. Can you go over what are these different layers that are fed, to the model and what they do?
Yeah. Do you mean specifically like in the prompt? for example?
Yeah, I guess the prompt, system prompt, context windows.
So in terms of what we provide to the LM, there's the system prompt, which includes often kind of instructions on the general task, maybe the persona that the model is intended to adopt. Frequently, kind of helping the model role play as a particular persona allows it to perform better on some task or another by sort of priming it to access the parts of its neural network that are maybe better suited to math or coding or data analysis or whatever the case might be. And then we also have the user message template, right? So the user message is sort of the input to the LLM. And that could be an actual user message from someone typing something into a chatbot, or it could be a document that you're kind of uploading or submitting, or it could be many of these in combination. It could be a user message, a document you're pulling from this document store. It could be a set of instructions you're pulling in dynamically for the country that the document and the user message are coming from. So that's all the context that we're pulling in. And then we have the instructions. We want to take all of these kind of inputs and then give the model very specific instructions on how to process them. So in this case, it may be to take the document, the user message, and the country kind of context and classify the request along multiple different axes, as well as draft a response. And maybe that goes to the right customer service agent in the right department who can then kind of review and respond with it, or however we might build this. And those instructions can include everything from what we might typically think of as instructions like do this objective, along with guardrails. So, don't do these things. Don't respond with emojis. Don't talk about our competitor, whatever guardrails you might have. And then also sort of thinking processes. So most people are familiar with techniques like asking the model to think step by step before arriving at an answer. We see that a technique like that really improves accuracy. But these thinking processes can get a lot more nuanced. So maybe the model needs to kind of create an analysis of disambiguation rules between certain classification categories and exactly how to think about that disambiguation, or what to do when a request doesn't fall into any of the categories. And those kinds of, I would say, are the various layers of the instructions. And then of course there's also tools. So if the model has access to tools, it needs instructions on when and how to use those tools. And those tools themselves have descriptions and instructions on, what they are and how to use them.
And the beauty of this, and I know it's also a beauty and a cursing, is that all of this is natural language, right? For the most part. And so, I think the next question, as probably, all of us on this podcast are engineers, and we are not used to this, right? We are used to like DSL or programming languages, which are, mostly very strict and procedural. Here it's like, hey, you can type whatever, plain, English or whatever your language is, and instruct the machine this way. So my next question is, how do you go about optimizing for accuracy and reliability on all these layers that you just mentioned?
So I think there's two principal approaches. So the first is you do it manually, which is, you're manually updating the prompt. You're trying to write these instructions, and then you're manually evaluating the outputs and the traces and seeing where does this fail and why. And I said don't use emojis and it's still using emojis. Why is it doing that? Let me try typing it in all caps. Maybe that will work. And then you run it again and it seems to work this time. But then 10 steps later, it doesn't work. So that's the kind of traditional process that I think most people are using today. And as you say, I think can be both very sort of, it's exciting, the kind of breadth of what we can operate over, but it's also very frustrating because it feels like building with quicksand, where it's very, very hard to get that kind of reliability that we expect out of traditional engineering. And the other way of doing this, which is, what I work on at Not Diamond, is optimizing the prompt automatically. And so essentially, what we do is we leverage LLMs in an agentic loop to iterate over hundreds of different prompt possibilities. And we guide this iteration using reinforcement learning over our evaluation metric. So, you can basically think of this as like, if you have your evaluation data set where you have an input and what the expected output is, it's almost like an algebra equation where you have 2 plus x equals 7, and you need to solve for x. Except here you have 2 plus, prompted model, input plus prompted model equals output. And so we're essentially iterating over the prompts for the model to maximize the, conversion or the transformation from inputs to outputs. And what we see is that this process is not only way more efficient than doing this manually. I think many prompt engineers can spend days or even a week or longer trying to do this in a manual way. And our algorithm runs in about 15 to 30 minutes of background processing. But on top of that, we also get a significantly greater accuracy than what we can achieve manually, because we're able to search over the space of possible prompts so much faster. And so we typically see improvements of anywhere from 5 to 5% to 500% accuracy improvements depending on the task. 5 to kind of 20-30% is the typical, but we've seen some use cases where we doubled performance, like the work we did together, and in some cases we even got 5-6x in improvements.
This number are just huge, and like when you hear these numbers, like there is no way you cannot go into optimizing all of this, instruction, system prompt, and so on and so forth. Like, it's just like you would not be doing your job well, right? If you are not getting into this. Indeed, for the listeners, Not Diamond and Rootly partnered on the Rootly AI Lab SRE benchmark, where we build a series of tests where we assess the capabilities of LLMs on SRE type tasks. Think Sweetbench, but for SREs. And for one of the models, we had 100% increase in accuracy. If I remember well, I think the Anthropic model were quite sensitive to prompt optimization, which may tell also how these models are built. Like, I think the OpenAI model tended to not have any gain of performance. So maybe the model itself is like already kind of trying to augment itself and optimizing itself, where Claude sounded like, you really needed to guide it. Can you give us like kind of a rough idea of the number of iteration that can go through, like a prompt optimization? Like, are we speaking, 100 of attempts, like 1,000 attempts? Like, how many times? And maybe there is not like, maybe it's a range, but I'm curious about that.
Yeah. So in our algorithm, we iterate over a few hundred requests in terms of the optimization loop. And so we actually recently updated this from our previous algorithm, iterated over a few thousand requests. But in this new algorithm, we're actually searching the search space much more efficiently. So, of course, algorithmically, we want to reduce the number of iterations to kind of most efficiently arrive at an optimal prompt quickly. But if you translate this into the kind of what a human would have to do to get to this, I think it's reasonable to assume that this is, somewhere on the order of, 50 to 100 or even more iterations over the original prompt, where small details are kind of being tweaked and tested and then continuously improved.
And what's fascinating is that it's not just like, you can have your model, and already using a model, it's very hard to find the ideal prompt, but also, for most companies who are using inference providers, this is also a quicksand, right? Because if you send the same, let's say the same input, the same set of instruction to different model providers, supposedly with the same model version, you'll get different answers. There is also a lot of model provider who will do kind of like silent updates. With that on top of it, like it's another layer of unknown, right?
Absolutely. I mean, imagine trying to build your application stack over components that were going to be deprecated in less than a year. It would be like hell. Like your whole life would just be running around putting out fires and trying to update components. But that's the reality that we live in with AI. These kind of models that are the backbone of this next generation of applications are regularly deprecated within 12 months of being launched. And you would assume that upgrading to a newer version of the same model at the very least wouldn't, negatively impact your performance. But the opposite is actually true, that OpenAI has estimated that about 30% of prompts will degrade when you try to upgrade the model. And some independent studies have found even higher percentages. It's very, very difficult to constantly be evaluating, testing, upgrading models, especially when, the goal is not to build, one prompt and then, continuously focus on it. People are building, dozens or even hundreds of AI applications and workflows across their surface areas. And the goal is to be able to allow these to remain stable once we've put them into production, and ideally continue to improve as the landscape improves. And right now, I think we kind of have the opposite scenario where there's this kind of constant sliding into technical debt that is very hard to manage manually.
Right. And as as a former SRE, I've been through the pain in like quote unquote regular software engineering of like, hey, you didn't pin the version of some library or package and, it's updated and suddenly, your application doesn't work. Or the fact that a software vendor or an open source software didn't communicate on a breaking change, or, a package that is not compatible with former, let's say route or instruction or whatnot. Here, this is basically becoming like, a constant change. Like it's almost the opposite, like you should expect your system to be constantly evolving and changing. So when users are using your tech, are they running it constantly, or is it more like of an ad hoc format?
Our tool is a design time tool, but you can automate it so that every time a new model comes out, you can very rapidly, day one or day zero, optimize your prompt for it and see if it actually delivers an improvement over the old model or not. And so that way you can kind of continuously improve as new models are released. So it's not continuous in the sense that it's not runtime, but we do see people reusing it over the same prompt as new models come out or as other parts of the system evolve and users want to kind of optimize their prompts again with maybe the new context that they're pulling in or other updates.
Speaking of users, do you have like any cool use case to share? Any specific application and results that you may have seen that are something like very concrete?
Yeah, so I actually right now I'm in Berlin for SAP's Tech Ed conference, where one of our customers and they were announcing GA for prompt optimization here, and so seeing a lot of pretty exciting examples of PwC had a use case where they went from 93% accuracy on document processing to 100% accuracy. So over their entire evaluation data set, after optimizing the prompt, they got every single input correct. I also saw a very exciting presentation from Henkel, the sort of chemical company, where they were able to take a prompt that, they wrote a naive prompt that, they didn't even spend any time really working on, that scored 0% on their evaluation data set. And from that prompt that was scoring 0%, they were able to get to a prompt that was scoring 80% accuracy in 15 minutes running the prompt optimization. We also work, of course, with a lot of startups. So one use case that I was really excited about was a rubric scoring use case where we're taking in a conversation and there's a rubric for scoring the conversation across many different dimensions. And the LM was scoring about 10% accuracy in terms of like perfect accuracy on every metric of the rubric, which was on 5-point scales. And this startup had spent months trying to improve this prompt. They'd hired a contractor to spend a few months just working on this prompt and wasn't able to get any improvements. And we were able to take them from 10% to 78% accuracy, perfect accuracy across all the scores. So those are a few use cases. Typically, we see people using us for RAG, for classification, for data labeling or data extraction, or really anything where there's a sort of a need for accuracy. So we see less usage in more creative applications or open-ended applications like maybe social chatbots. But those are some of the examples that I was excited about recently.
Yeah, thanks for sharing. I think there has been a lot of noise about, some survey done. I think it was by MIT about the number of projects that are abandoned because oftentimes you can get very easily to a prototype, but then these few missing percent are just not they are just out of reach, and because of this, you just cannot move forward with deployment. And sounds like in at least one of these cases, you were able to push and even to 100%, which is very impressive. So I think moving forward, obviously we are very early. AI and LLM and transformer have been around for a while, but truly in the last 2 to 3 years is when the industry has really been able to benefit from them. We know we are very early in the history of this technology. Do you think that, I want to call it almost an art, it's more of a methodology? Of course, there is some rules and principle about it, but do you think that this prompt optimization is something that is here because the technology is not mature? Or do you think it's something that's here to stay because of the inherent, nature of LLMs?
I guess I'm biased because I'm working on this, but the reason why I'm working on this is because I do believe it's here to stay. And I think that there's a couple reasons for this. So first of all, LLMs are inherently, non-deterministic, but not only that, just the nature of LLMs is that they're trained over this fuzzy space of natural language. And every model is trained differently with different training data and different training procedures. And so the way that it transforms inputs to outputs will be different. And that will always be true. And it's the same with humans as well. I mean, the way that humans interpret and, transform words into other words is very different from human to human. And so I think it's also interesting to just observe that, a few years ago, when this concept of prompt engineering came out, there was a lot of kind of denigration that this was going to go away. The models were going to get better. They were going to understand the instructions. And the opposite is happening. I mean, now every time a new model comes out, the providers publish very long prompt engineering guides on how to use them and how to upgrade your prompts and what words to say and what techniques to use. It's only gotten more and more laborious, especially as, we also haven't really converged towards this world where everyone's using one giant model for everything. We're using many, many different models, and there's more coming out all the time. I think the last piece is that these systems, even on top of the natural language, there are so many parameters that go into these systems. And I think it's a little ironic that as an industry that, we're turning all these knobs and dials manually to kind of control the outputs of these AI systems, when historically AI was invented to turn all of these knobs and dials automatically to manage high variable or multivariable systems. So that's exactly what, machine learning was built for. It's what AutoML was built for. And I think the same is going to be true as we, continue advancing in the world of generative AI.
Mm-hmm. In some way, do you think a parallel can be made with SEO, where every time Google was updating its algorithm, marketer, and we're trying to understand how to play well with the latest update?
Yeah, I think so. I think there's the analogy I think makes more sense to me is the AutoML analogy, where we have in the last decade algorithms being built that could automatically optimize the parameters of our machine learning training systems. So everything from how much data we were using to the search algorithms, the number of epochs in the training cycle, and that just proved way more efficient than doing it manually. I think today we probably are a little bit more in the SEO kind of world of like chasing and trying to manually kind of interpret the black box of the search algorithm. And I think we're much better served by doing that in an automatic way.
Thomas, if people want to get in touch with you on the internet, where can they find you?
So I'm on Twitter at Tomás_HK. I'm on LinkedIn, Tomás Hernando Koffman, and you can also email me. My email is t5@notdiamond.ai.
Great. Thomas, thank you for coming on the podcast.
Thanks so much, Sylvain. Great chatting.